All right, welcome today to NLP. To start off, were there any questions about? Were there any questions about the course so far? About groups? About anything like that? Who here is already in a group? Who here is going to get in a group by Tuesday of next week? Everybody raise your hand. So what are the rules with regard to groups? How many people per group? Four. Who can you form a group with? Anyone. Anyone that's enrolled in any section of this course. Graduate or undergraduate. Does not meet or section A, anyone. So, any other question? How do you find people to be in a group with if you don't know anyone? Piazza. So use the find teammates function on Piazza. Find teammates. Do it soon. Otherwise, we'll kick you out of the class. And I'm only partly joking. Other questions? I saw somebody with a hand up. Did you?
Yeah, I was actually going to ask how you find members. I guess.
Yeah. Or jump on people after class. So I just want to introduce myself. I'm David Mortensen. I'm a systems scientist in the Language Technologies Institute. I do not have a cute Scottish accent or a long beard. I sometimes have a short beard. So I don't have a cute Scottish accent. And I'm not cute in any way, except when I try to speak Chinese, in which case I am adorable. I love teaching this course, and I'm excited to be here with you. And I'm excited to talk today about some applications of NLP. This is going to be an important lecture because, and we put it number 2, because it's a lecture where we talk about question answering, which is half of what the project is going to be on. So the idea is to be able to get you started with the conceptual framework for the project right at the beginning. So pay attention, because this will come back to haunt you if you don't. So if you're doing NLP, what are you doing? Or to back up a little bit, what are some reasons why you would want to do natural language processing? Every semester, somebody comes into this class and says, I'm from Tepper, I'm in the computational finance department, and I want to take your class. Is it appropriate for me? What is that person interested in?
Money.
Yes, money. That person is interested in money. Yes.
Because there are a lot of financial data daily, and you need to summarize all the financial data, and you want to know, okay, what's the big trade or what's the interesting thing today, so you can make a decision of investing.
Yeah, so there's all of this financial data that's in the form of reports of various kinds, and you want that information in a way that you can reason about computationally. You probably want it in a structured kind of way. You don't just want, you want to be able to extract out of this mass of written reports these numbers and the relationship between these numbers and other things, right? So you can then use that data to make money. So this is part of, there are other things that you might be interested in doing, like sentiment analysis and so on. But this is part of the task that we refer to as information extraction. Basically, the idea is that you have a bunch of text, you have a corpus of text, and you have an empty relational database or some other kind of database, and you want to populate this database from what is in that corpus of text. How do you do this? Well, with information extraction. Here's an example, a somewhat dated example that I inherited from my progenitors in the early 2000s. So say you have this text, and you have a database that has the field state, party, candidate, and fraction. You want to extract for a particular state and a particular political party what candidate earned what fraction of the vote. Then information extraction at a high level is the task of taking this text and producing this database, this table. So we're not going to tell you how to do that in one step, but we're going to talk about some of the steps to do that. And my favorite of these steps, because I've had the opportunity to work on it a certain amount, is named entity recognition, or NER. NER is basically the task where you have a text and you want to identify all of the proper nouns that fit certain criteria within this text and tag them. So usually the proper nouns that you're interested in are things like names of persons, organizations, locations or geopolitical entities, facilities, times, and so on. So this is kind of what, if we took this text that we were talking about earlier, and we did NER on it, this is sort of what we would get. So Senator John Edwards is a person, Democratic Party is an organization, Florida is a location or a geopolitical entity, and so on. So just identifying these entities that have names, this is named entity recognition. Well, that's all fine and good, but what good is it to know what entities, which spans within a text or entities, if you don't know who those entities are or what those entities are? So this is another task that builds on named entity recognition. It's called reference resolution, or it's sometimes called linking, entity linking. So basically, you have a knowledge base that is a representation of what things are in the real world. A lot of times people use Wikipedia. So let's say this is the Wikipedia article for John Edwards, whoever he was, once upon a time. He's an adulterer, that's what he is. We have done NER on this text, and we have Senator John Edwards, and we have Edwards here. And both of those, we want to link to this Wikipedia article for John Edwards. That's what reference resolution is, or entity linking. So that's related to co-reference resolution, but it's different. So reference resolution means you have an external knowledge base. You're trying to link entities within the text to that external knowledge base. Sometimes you don't have an external knowledge base, and that's not really what you're interested in doing. Instead, you're interested in identifying what named entities within a corpus refer to the same real-world entity. And this is called co-reference resolution. So in the reference resolution slide, we had Senator John Edwards and Edwards both pointing to the same Wikipedia article. here we actually just have them linked to each other. That's co-reference resolution. There's a related problem, a related kind of co-reference where you have not just named entities, but also like pronouns, like he or they. And so you can also do co-reference resolution with these. So you link together all of the things that refer to the same entity in one chain. Many of you will use this in your project. So there are tools for doing this, for doing co-reference resolution. And you will use this. So you should pay attention. You should write something down. Remember co-ref. Anyway. Another thing that you might be interested in order to get this kind of relational table that we were talking about before, is relation detection. So we might be interested in what political parties these different candidates belong to. So we might have a member of relation, and we want to populate that relation. This is relation detection. So we can, from this text, figure out as humans that all of these candidates are members of the Democratic Party. And yet it's challenging actually to do this computationally. Because you have to use a lot of knowledge about the world in order to do that. But this task is something that we'll talk about later today, and we'll talk about a way of doing easy cases of relation detection, a technique for handling that. But first, let's talk about NER. When we're tagging named entities, we tend to use a kind of representation that is either called BIO or IBO, or IOB, sorry, IOB or BIO notation. So basically, we take the text and we tokenize it. That means that basically for every word or punctuation mark, there's one token. And we put those tokens in one column. And then in another column, we put a tag. If the token is not part of a named entity, if it's not in a named entity span, then it gets the tag O for outside. If it's the first, the first token in a named entity, like in Air Force, air is the first token, then it gets B for beginning, and then org for the type of the named entity. And if it's inside of a named entity, but it's not the first, then it gets I for inside, and then the type. So this allows you to unambiguously, as long as you don't have nested entities, as long as you don't have an entity that's inside of another entity, then it allows you to unambiguously identify all of the named entities in a text. So basically, the task in named entity recognition is, given this sequence of tokens, to get this sequence of tags. So really, it's a kind of what we'll call a sequence labeling task. Because you have a sequence and you're trying to label all of the items in the sequence. we'll talk about different strategies for doing this in the course of the class. So different machine learning techniques that have been used to do this, HMMs, CRFs, and so on. In some sense, it's also a classification task because you're given a token and you're asked to say what class it belongs to. And we'll talk about classifiers and what classifiers might be appropriate for this kind of task. So here are some examples of some types of named entities that are commonly recognized and are important. Persons, organizations, locations, geopolitical entities, facilities, natural phenomena. What would a natural phenomenon be that we might be interested in like a hurricane? They have names, so we want to be able to tag them sometimes. So the truth is, there's no master list of named entity types. Different tasks call for different sets of types. And different data sets that people use will have different sets of types. So one of the most common, one of the most important NER data sets actually uses these first four: person, organization, location, and GPE. What is a GPE? Does anybody know what a geopolitical entity might refer to?
Countries.
Like countries. Countries are an example. Yeah.
I guess like organizations of countries and like different treaties or trade routes.
That's not how it's actually used. To some extent, yes, but
Maybe something like the UN or like individual country governments.
yeah, like individual country governments in particular. So a geopolitical entity is something that has a government, population, and a border, an extent. So a country is a geopolitical entity. A city is a geopolitical entity. A province or a state is a geopolitical entity. But like Asia is not a geopolitical entity because there is no Asian government yet. So how do you tell whether your NER system is good or not? We go through, we assign these labels. How do we know whether we're doing a good job or a bad job? How would you tell? What numbers, what metrics might you use to decide? F-score. Okay, why F-score? What is an F-score, first of all?
I think is because organization and location is only a small part of the full text. So take an example. There are many O inside the text, and we don't know. And if all the thing, if the 90% is O, and we tag 90%. 95% of O, and the occurrence is still high. So we need an F-score to determine what is the mainly tag.
Sure, you're dealing with relatively rare
Yeah.
events, the things that are not but let's back up a little bit and ask, what is an F-score? F measure. What is F1? Who's heard of F1 before? Okay. Who has heard of precision and recall before? Okay. What is precision? In the if you're evaluating a classifier, let's say.
True positive divided by true positive
Yes. So in other words, as your oh, that's disturbing. As the number of false positives goes up, your precision goes down. So precision, you do good on precision if you don't guess that lots of things are relevant that are not. You know, you precision favors not having lots of false positives. So what about recall? What is recall? I don't recall. Now what is recall? It's like the opposite of precision in a way. So if you do well, if getting false positives hurts your precision, getting false negatives hurts your recall. So you don't want to miss anything. If you miss something that's relevant, that hurts your recall. So that's precision and recall. Why do we care about these two things separately? How do these present a different picture, than if we were to just compute accuracy? Yes.
Because looking at them separately allows you to figure out whether your model is like, or I guess like what you're define your model is. Like for example, maybe you're being like too lenient in your classification, and as a result, that would probably mean that your recall is better, but your precision is worse, and then you're just like labeling everything.
Right. Right. It's really essential if you're trying to do error analysis and you're trying to make your system better to know what kinds of errors you're making. And precision and recall allow you to distinguish the types of errors that your system is making so you know how to fix your system so it doesn't make those errors anymore. Yes?
Would it ever be useful to distinguish between like classifying them as named entities versus like classifying what specific type of named entity?
It does make sense to sometimes do that. And so usually, if you get the type wrong, then it's considered a false positive. So if you guessed correctly that it's a named entity, but you incorrectly guessed that it was an organization instead of a location, then you would then this would count as a false positive, and so it would hurt your precision. But it might be useful in some cases to actually have, a type-based metric, that took that into account, that distinguished whether you're getting the right type and whether you're getting the right tag other than the type. And there are metrics that measures that do that. But people mostly use precision and recall. So if this is precision and recall, what is F1?
To precision, multiply the recall and divided by recall and precision.
Yeah, so basically, to put that another way, it's the harmonic mean of precision and recall. So that means that you're taking both precision and recall into account basically equally. And this is the most common measure that's used for these things. So if you read a paper that's about named entity recognition, they're going to report precision, recall, and F1. So how do you build an NER system? Well, of course, that depends. You know, there are different technologies for doing this, different approaches. But this is sort of the canonical approach. And if we ask you on a test, not that we will have tests, but if we were to have tests, and we were to ask you what is the canonical approach to named entity recognition, this is what we would be referring to. So basically, you start off with a collection of representative documents. You start off with a corpus of documents that you think is representative of what you want your named entity tagger to work on. So it's the right domain, you know, it's likely to have similar named entities, similar in other respects. Then you have humans. This is the expensive part. This part can be expensive, but this part is much more expensive. Where you have humans go, and you have humans identify all of the named entities and their types in the representative document collection. Why do we do this? It's because we don't like humans, right? And we want to punish them. So we want them to have meaningless lives. So we pay them to go through lots of documents and mark them up like named entities. Now, why do we do this? We need training data. We need these annotated documents. So we're assuming a supervised approach to named entity recognition. There are unsupervised and rule-based approaches to named entity recognition as well, but that's not the canonical approach. So we get these annotated documents, our training data, and then we extract features from them, and we encode them in BIO or IOB format. What are we talking about when we say feature extraction? What is feature extraction? What are features? Yeah.
Would they be like the specific properties of like the text, like the sentence length and like words and stuff like that?
Yeah. So you might be interested in, sentence length. But certainly you would be interested in what words come before named entity, what words come after the named entity. You might be interested in whether those occur in particular classes. You might also be interested in words that occur inside of named entities. So for example, if you have the word river, then this is going to occur a lot of the times when this occurs, not all the time, but many times when river occurs, it's going to occur as part of the name of a river. Well, like the Mississippi River, the Monongahela River, the Ohio River, the Allegheny River. So you might have a feature that corresponds to the word river. And you can use that to train a classifier. It turns out for named entities, for named entity recognition, there's some very important features that you probably are aware of. So if you're looking through a text and you're looking for proper nouns, just in general proper nouns, not necessarily named entities, but if you're looking for proper nouns, what do you look for? Yes?
If it's English, you can look for capitalization, but
Yeah, so you can look for capitalization, you could look for the presence or absence of determiners, which are words like da and da. You know, so does not occur very often with the identities. You know, there are features like this. And by feature extraction, we mean you go through all of this data computationally, programmatically, and figure out for each token whether these features are true. And then you could use these extracted features to train the model. So we have the extracted features that gives us basically the training data. And then we train the classifiers. We're basically doing a multi-way sequence labeling task. And the classifiers could be MEMMs or CRFs, which are conditional random fields, SVMs, which are support vector machines, HMMs or hidden Markov models. We'll talk a lot more about hidden Markov models than we will about CRFs or SVMs, although we'll talk about SVMs some in the classifiers lecture. So we've got these classifiers that are doing sequence labeling. That gives us our NER system. So we can then give new text to this NER system, and it will give us back a sequence of labels based on what it thinks the named entities are. That's what your textbook says, but that's really not the whole story. So you never just do this. You always then evaluate precision and recall. You evaluate your NER system using test data. And then you probably go back to this stage or this stage, you know, and refine until you are satisfied with your precision and recall, and you can publish your paper in ACL. So let's talk about relation extraction now. Relations. Well, what are relations? Mathematically, what is a relation? It's a calligraphic R, right? What is a relation? Okay, it's kind of function, or it's more general than a function. So functions are a relation. Yeah.
It's a ordered pairs.
It's a set of ordered pairs. Set of tuples. Or tuples if you're a barbarian. So basically, you could have a set of ordered pairs that describe geospatial relation, like proximity. So near or on outskirts. So let's think about near. So the near relation includes the set of all of the things that are near the things, right? So all of the every x that is near some y. So how would we go about figuring out what relations are encoded in a particular corpus? You're given this task. Let's talk about the married to relation. You're given a big corpus of text, and your task is to tell me who is married to who. Yes.
Search for the term married to across the corpus of not the one that's still left.
Okay, that would be one place to start, right? So you could start with a pattern. You could start with a pattern. X is married to Y, or even a set of patterns, right? So what other patterns could indicate this spousal relationship?
I also want to look for the words like husband and wife, this type of things.
Yeah. So you could use other kinds of patterns. You could say things like X is the husband of Y, or X is the wife of Y, or X, husband of Y. So you could come up with some set of seeding patterns like this. Is that going to get you all of the ordered pairs that are attested within the corpus? No. So that's going to get you started. So let's say you come up with a bunch of these patterns. And you search through the corpus, you apply all of these patterns, and you come up with a bunch of ordered pairs based on these patterns. What are you going to do next? Yes? But you could use it as training data, but you could use it at an even simpler level for searching again. How might you use that to search again? So now you have a bunch of patterns, you have a bunch of names, and a bunch of tuples. How could we use those tuples to get more tuples? Don't look at me so sadly. There is a way. What if you go through the corpus, and every time the members of those tuples occur in proximity to one another, you identify that as a pattern. And particularly if that pattern occurs more often, you add it to your, or more than one or two times, you add it to a collection of new patterns. Then you use those new patterns and go through the corpus again and collect more tuples. Then you use those tuples to make more patterns until you found all the tuples.
Is this
Yes.
depending on people being referenced multiple times, like saying this is the wife of this, and those same people are being referenced later under a different pattern?
It doesn't.
How else are you getting the new patterns?
It doesn't necessarily depend on that. No, the new patterns are just like if you started off with patterns like X is married to Y, and well, it is. You're right. It is actually dependent to some extent on the same people being referenced multiple times. That's correct. So this is the bootstrapping approach to relation extraction. You start off with either seed tuples or seed patterns, and you proceed from there. Seed tuples give you a tuple set to work with. You search for those tuples. You extract patterns based on those tuples, and you add that to your pattern set. You then search for those patterns extract the tuples, you add those to your relational table, but also to your tuple set, and so on. So this is very simple.
So when you're searching for more tuples, like say you have like Mary is married to John or something,
Uh-huh.
would you use that to search for more like Mary and John occurring together, or would you search
Yeah.
in general for like more person occurring together?
You would search for, so if you had Mary is married to John, then you extract the tuple Mary and John. Then you search for spans in which Mary and John occur together, and you take those as evidence. You take those as patterns that you can then use to search for other tuples where X is married to Y.
Why wouldn't you want to like take all your tuples initially and then like label them as the type based on the pattern? Like you would label everyone that occurs with married to as people, and then just search for like people tuples instead of like just the same tuples you saw in.
I'm not sure I quite follow.
Like, couldn't you do an intermediate step where you label the types of the nouns in the tuples? Like if you had your patterns beforehand, you knew married to is a relation
Uh-huh.
in which both members were people.
Right. Oh, okay. So you're assuming you're doing something like named entity recognition first.
So, I guess.
Yeah. So you could do that. Yes. Yes. And that might allow you a greater level of generality, for the patterns. What problems do you see with this approach? Not with your approach, but this approach. Yes.
It could end up getting a lot of false positives.
Yes.
It makes one mistake and just keep on playing.
Right. You have error propagation, right? So if you get one thing wrong, that it could explode. Yeah. Anything else? So there's one problem that's just a problem with relation extraction generally. Yeah.
The two tuples that are very close together, how do you map which one do you map?
Yeah, that's actually a problem with this approach. Yes. So like defining patterns when you have two tuples within the same window, you could end up with kind of contradictory even relations, right? Or polygamy. Any other problems? What about divorce? Is that a problem for this approach? So we kind of assume that relations are stable. But, our approach has no way of capturing temporal aspects of these relations, right? So that's a weakness of not just this particular approach to relation extraction, but to approaches to relation extraction generally. Any other questions or comments about this before we move on? You good with relation extraction? So from time to time, I've been known to ask a test question on this subject. So just bear that in mind. I consider it to be somewhat important. But not as important as information retrieval, because this relates directly to your project, and you need to know about it definitely, not just for the test, but for other things. What's information retrieval? What is the task in information retrieval? What does it sound like? So if I have a big corpus of documents, what is the task of information retrieval? Yeah.
Trying to answer a query over this corpus of
Yeah.
informational query.
Yeah, informational query. You know, the most simple type of query that you might have is, you know, you might want to know which documents are relevant to the query. So search engines basically do information retrieval, but there are other information retrieval tasks that are more nuanced. So one basic tool for information retrieval is what's called the vector space model. This relates to, you know, as we formulate it here, to the idea of a bag of words. What is a bag of words? What is a bag, computationally speaking? How is a bag different from a set? Yes. You can have duplicates. It's like a set, except you can have, it's like a multi-set. You can have more than one of the same item. So a bag of words is exactly that. It's a bag, it's a set, or it's like a collection of words where you can have more than one of the same word.
That you don't care about the orders.
You don't care about the orders. It's unordered. You only care about membership. So one approach to information retrieval tasks is this kind of bag of words approach, where you treat a document as a bag of words, and you treat a query as a bag of words, and you try to select the document that best matches that query. So one way of representing this is to think about the documents and the query as multidimensional, as sigma-dimensional vectors. So let the size of the vector be the size of the vocabulary in the of the language, you know, of the corpus. You know, let it have that number of dimensions, and let the value of each dimension be the number of times a particular word, that corresponding word occurs within that document or within the query. So you have these vectors. Then you can compare the similarity of these vectors. How would we compare the similarity of two vectors of this sort? Yes?
Cosine similarity?
Cosine similarity. Why wouldn't we use dot product?
Sensitive to the magnitude.
Yeah, dot product also allows us to compare the similarity between two vectors, but it's sensitive to the magnitude of the vector. Why is that not what we want here?
Not information that's relevant to it.
Yeah, so the magnitude is kind of irrelevant. We're concerned about whether the vector is kind of pointing in the same direction. We're not concerned about how big the vector is. I mean, how great the magnitude of the vector is. So here we have cosine similarity. Well, that's pretty good. That's okay. But what about the fact that some words occur a lot and are not necessarily super relevant to what you're asking about, and some words occur infrequently, but they're more relevant in a way In other words, they're more informative about whether the document is relevant or not. So if you're searching for your query is something like, are elephants happy? Other things being equal, are and elephants and happy are all being treated as equally important. Why is this a problem? Which of these words is most frequent? Rank the words according to frequency.
R.
R is most frequent. Then happy. Then,
Elephants.
but what is my query really about?
Elephants.
So we need some way of dealing with this. And the most common approach, although it's sort of mathematically suspect, the most common approach is to use TF-IDF weighting. So you weight cosine similarity by TF-IDF. And it lets you deal with this fact. Because elephant is infrequent in the corpus as a whole, but probably relatively frequent in those documents that are relevant to the query. And that's what TF-IDF gives you. So let's talk about question answering. Now that we've talked about information retrieval, because actually many of you will use basically information retrieval techniques in your question answering system. And this is sort of a standard question answering system, and it uses that. So you start off with a question, and then you process that question. You make a query out of the question by giving it a vector representation, and you also classify the question. You say, is this a binary question? Is it a WH question? Is it a question about a person or an organization or a location? You classify the question. So then on the one hand, you go and retrieve your document. You assume that beforehand, you've taken a whole bunch of documents, a whole corpus of documents, and you've indexed them so they're easy to search. Otherwise, this is very inefficient. And basically, you retrieve the documents that are most relevant to the query. How do you do that? How do you know which documents are most relevant to the query? Cosine similarity, probably TF-IDF weighted cosine similarity. Okay. So that gives you a set of relevant documents. Are you done? So far, you've just done information retrieval. You haven't really answered a question. How do you get from having a set of relevant documents to the answer? So first, we've got to retrieve passages from those documents. The whole document is too big to return as an answer. We want something smaller than the document. We want passages within the document, like sentences. So we look through all of the documents for those passages that have the highest relevance to the query. So you've selected the documents that are most relevant to the query, and then you're going to select the passages from those documents that are most relevant to the query. That gives you a set of passages. Then is our work done? Then the fun begins. So is a passage really an answer to a question? Google sometimes thinks it is, but it's not. You have to process the passage. And that's what having this question classification helps us to do. It's to know what it is in that passage that actually is the answer to the question. You know, am I looking for the name of a person? Am I looking for a location? And so on. That gives us the answer. Does everybody understand this pipeline? Now is a good time to ask questions if you don't. I promise you your peers will not think less of you, even though they're highly judgmental CMU students. So this is actually what you'll be doing. This is a little bit different than in the project. This is a little bit different than this architecture we discussed here. So rather than having a corpus of documents, you just get one document. You know the document. Your system just gets handed one document. You have to retrieve the appropriate passages, process the answer, give the answer. You also, in a different task, have to take the document and generate questions. And so you take the document and generate questions, and those questions are then fed to other people's question answering system. So you want to generate hard questions in order to make life more difficult for your peers, because you hate them. Because you love them, you want them to work hard and develop. So this is what you'll be doing in the project. Questions about that? So it's simpler, but the same idea. Yeah.
I remember like the project mentioned it's the document is unknown.
Yeah.
So
it's unknown to you. It's by known document we mean you don't have to select a document out of a corpus. We just hand you a document. It's not known to you beforehand. It's basically going to be a Wikipedia article, and we're going to select a set of Wikipedia articles on some topic, and you won't know in advance what those are, but we'll feed each of these articles and the appropriate questions to your system, and your system will be charged with answering them, or with generating the questions and with answering the questions. Does that make sense?
yeah, so we are meaning like we know in the last what kind of topics and documents are, so we can train our algorithm in these space.
You won't know the topics beforehand. You should do something. You'll know the domain, so you'll know, it's an encyclopedia article, but you won't know the specific topics. So you want to be rather general and robust in your approach, rather than trying to be overly specific or to target a particular topic. So for question answering, the usual metric is mean reciprocal rank, and the formula is given here. Basically, your you do well if the first correct answer to the question I is high on the list. It's not particularly complicated, but that's basically how it's evaluated. So you have a bunch of questions, T questions, and you have the sum of all of those over the, or the product of the reciprocal of the number of questions multiplied by the sum of the reciprocal of the rank of the first correct answer. Okay. To do information extraction and these related tasks, then there are some very general tools that you can use that are relevant. So one is the idea of supervised classification. Now, just to be clear, what do we mean by supervised? Does everybody, what is supervised classification as opposed to unsupervised classification? Yes?
Maybe like when you put the data into the algorithm, supervised, and then you need to make annotations in the data.
Yeah.
Supervised is just put the data in without any annotation.
Yeah, so, yeah, kind of. So for supervised classification, you train a classifier with labeled data, right? And then you can use it on unlabeled data, but you have to you have to have training data that is labeled. So for named entity recognition, you have to have training data where you've labeled all of the named entities with their types. For information retrieval, if you had a supervised approach, then you would need to label documents for relevance and then train on that. That's not the approach that we've described. Is not a supervised approach. So, what are some examples? Do you know of any examples of supervised classification? Yes. Like what?
Classifying images of numbers.
Okay, classifying images of numbers. This is typically done in a supervised fashion. So what is the process?
So you have processing data that is handwritten digits.
Uh-huh.
Someone else annotated. Feed that to your model. That's the model that the model learns the representation of the
On what?
data that it hasn't seen.
Right, on unseen data. Yeah. So most classification algorithms that we would use in this class are supervised classification algorithms. You can also view clustering algorithms as being kind of like classification algorithms, although they're unsupervised. But mostly we're going to talk about supervised classification algorithms. So we'll talk in particular about naive Bayes, because it's very simple and easy to understand, and you'll do a homework assignment on it. But we'll talk about other classifiers as well. So we'll talk about SVMs, or support vector machines. Nice kind of classifier. You'll talk about perceptrons and about other kinds of neural classifiers as well. And in fact, we'll do a homework assignment that's on a classification task called sentiment analysis, where you're using a neural network to classify reviews into categories based on the number of stars, like Amazon reviews. So this is supervised classification. You need neural classifiers, SVMs, naive Bayes classifiers are all supervised. So that's something to keep under your belt. Another idea that is important that we've brought up here that will come up again and again is feature vector representations. How has that come up in our discussion so far? What kind of vectors? What were our features? Think bag of words. If our vector is the bag, our features are the words. Anyway, word vector. Word vectors. So this idea in different forms will keep coming back. And it's a very powerful idea and something that you should make sure that you understand and that you can employ. Because it will be hard to do the project if you do not. Another idea that we've brought up that will be important to you later on is the idea of bootstrapping. What is bootstrapping? So this is an example of bootstrapping. What do we mean when we talk about bootstrapping? What is the metaphor? It comes from the expression, pull yourself up by your bootstraps. So what is the idea? Yeah, yes, you start with a little bit of labeled data, and based on that, you bootstrap. You label more data that you can then train on to label more data. That's bootstrapping. So that will be an important idea, so you should keep that in mind. Perhaps most important of all, I would say, of the things that we've talked about today, other than question answering, is evaluation. Precision and recall will come up again and again. So be sure you understand them, you remember which one is precision and which one is recall, and you know how they relate to F1, the F manager. Mean reciprocal rank is also a good thing to know, but it's important to know, to have in mind the idea of evaluation metrics. So we have consistent ways of evaluating systems so that we can compare and know which ones are better than which others. And you will use this in your project as well. You'll need to do evaluation to know whether the changes that you're making to your system are actually improving or making worse or having no effect on the performance of your system. So this is very important. Any questions? Yes?
I just want to ask about feature. I want to check in on some correctly. So we feature, for example, there is one entity and there are several words which are really related to this entity, so that's like feature.
A feature. So a feature refers to something that is to a value that is used by a classifier. So or used in some other way. So if you take a document and you take a corpus of documents, and for every word in that corpus, then you have one dimension in a feature vector. One dimension in a vector that corresponds to each word. So each of those dimensions would be a feature that could be referred to, whether you're using it as a with a classifier, or whether you're computing cosine similarity or whatever. Essentially, each you're factoring out from those documents specific values that you can then use discretely. Although you can have continuous features as well, but that's the idea. So by feature we just mean that. And when you're doing named entity recognition, then you could define a set of features. It could be word vectors, but they could also be other things like capitalization. For each token, you might have a vector of features, and one of the dimensions might be is capitalized, and one of the dimensions might be is alphanumeric, and so on. And so those would be used by a classifier to decide whether a particular token is in a named entity or not. And that's what we mean by features. It's a way of, yeah. I can't hear you.
So like in bootstrapping, when you assign labels to where can you bootstrap the assignment?
Yeah, that would mean exactly that. And that's what we were talking about earlier, with the problem of error propagation in bootstrapping. So it can happen. You can incorrectly label data, and then based on that data, you can incorrectly label more data, and based on that, you can incorrectly label even more data, and so the errors propagate. So that's a problem with bootstrapping approaches. Well, what would the advantage of bootstrapping approaches be then? Yes?
You don't need a large corpus to get started.
You don't need a big set of training data. So if you have limited training data, then bootstrapping approaches can be very attractive. Anything else? Okay, I will see you Tuesday.